Hello there. It's been a long time, about 6 months, I guess. Today I'm not going to be talking about any fancy feature of programming languages. I'm going to mostly be talking about something simple. I'm going to be talking about how to execute code, not in the way of like how to implement an interpreter, a compiler, but actually how code is executed. Of course, I'm not going to be talking about all programming languages. So mostly here I'm going to be focusing on a class of languages called strict languages. And yeah, let's start. So most people, they have this impression that code is executed line to line, okay? So if I have a line print and line hello, word, tutoru, one after the other, right? And if you change it, the order that is gonna show changes. That is a misconception. That is like an actually big misconception. There is an execution strategy, so it's executed in a specific way, but it's not strictly like line to line. This may be true for something like assembly or Fortran, but that's mostly not true for any other programming language. So that's not true for even something as simple as C. A good example of that I can show you here is let's make a function. The function does not care about the parameters. It just accepts 3 parameters, and I'm gonna be calling it with this, right? So what is the printing order? You may be like, oh, it's gonna be left to right. See, it's already not line to line. But let's say it was like this, just to make it easier to visualize. Let's execute, and the printing order is actually the opposite. That's an implementation detail of a bunch of stuff. And you may be like, okay, why is it executing right to left? Because you can see first tutoru, then word, and then hello. Implementation detail, it's the case for Camel. It's the case for, I think GCC, which is the GNU C compiler, also does that. We can also try it in JS by doing a function that does not care about its parameters. In JS you can do this. Here. And let's call it with console.log hello. Console.log word. And console.log tutoru. As you can see, in JS it's executed left to right. So some languages do left to right, others do right to left. But the most important thing is all of them do there is one thing that all of them are going to be doing in the same order, which is all the arguments are executed before the function itself starts. Okay, this function just say f started, okay? And as you can see, f started is the last thing to happen. I can do the same in JS. Okay, and run it again. You can see that while the arguments are running in a different order, so in OCaml it's right to left, in JS it's left to right, the parameter, the function itself only starts when all the arguments are done. This is one of the, this is probably the core property about what is described as a strict language. A strict language is a language where the arguments are strictly evaluated before its body, okay? That may not be true for all languages. If any of you know Haskell, Haskell is known to be a lazy language. Haskell does not have side effects, so you cannot inspect that. Like this only matters, the execution order only matters if you have side effects. So like printing, Haskell does not have such a thing. Like Haskell is not a real programming language. But Haskell is a lazily evaluated language, which means the order of execution is not as simple as that. But yeah, this is a strict language. In general, the way to think about it is programming languages are a thing called a rewriting system. Essentially, they delimit on how can your code be rewritten. Because you may think, oh, isn't this the same as doing this. Again, we had a video on the lambda calculus. So you may be thinking, isn't that the same as this? Because, yeah, you can just move. And in this case, yes. But that's not always true when you have side effects. The arguments are still always going to be executed first, but you cannot just change it in any order. You may think about it as a mathematical thing. So if you have, I don't know, let's say we have a function f, which expects x and do x plus 1. And then it does, let me make another function, g, which is x plus 2. And so this does this. In normal math, and let's say you had this, you could just start first by, oh, I have a better example. Let's say you had this. How would you simplify that? Rewrite it. Reduce it, maybe. I'm not sure the word. In general, you would do this. And then expand it. So this goes here, which means x goes here. And then the next step would be to look at g. And g is x plus 2. We know that x is 5. So that would be 5 plus 2. This is a strict evaluation. You can see that always I resolved first the argument, and then I expanded the function so to reduce it further. There is no need for this. In normal math, you can easily do it in a different order. You can, let's say you had this. You can say that this is the same as this. Notice, I did not execute the parameter yet. And you may be like, oh, right. So I can also do the same stuff here. So this would be plus 2. And while both of them have the same value, so here it's 8, here it's also 8, that's not true in a programming language because the order may matter. So if I don't execute it here, I may not have a side effect. This is the simplest model to keep in mind, which is code is executed, first argument, and then the body. And then you need to remember that about everything is a function. So if you have an addition, okay, an addition is a function. It's actually this. So it's adding 1 plus 2, and then adding the remaining, which is 3, to 3. What is going to be executed first? First, camel the right parameter, which is 3. So there is nothing to do here. Then it's going to execute the left parameter, which is 1 plus 2. Again, then 2, 1, we have 3, and then 3 plus 3 is 6. But you can see that it only stops when it gets to something called a value, when it's not reducible anymore. Why 3? Like, why stopping at 3? So again, first it would do 3, and then it will do here, and then of course it will do 6. But why does it stop at 3 plus 3? Like, why does it stop when this is 3? I think if I make this a function, it may be better. So if I say add like this, 3 plus 3, like, why does it stop here on 3? And the reason is that's a thing that cannot be reduced anymore. Like, that's a value. That's the simplest thing that you can have, essentially. You may, if you had an additional function here, so add 3, 5, it would execute it. But there is no function anymore. It just stops. And then as soon as it stops on all the arguments, it expands the function and be like, okay, now we are going to be doing the body of the function. This ensures that I can predict the order of this. So I can show you that this is the case by doing A and B. And he's complaining about the X here. I'm going to be doing this just to show. And I need a new line. As you can see, it's 1 plus 2, then 3 plus 3. So, and if I did 3 and 4, again, right side first, 1 plus 2, then the left, and then it does the return of both sides, which is the argument. This is simple here. It gets more messy because you may have something like a callback. So let's make a very simple function, which is very common, which is map. This map is going to be mapping a list. So empty list goes to empty list, element, we do TL, and then FEL to TL. So this function maps something. It maps a list. Is it right? Oh, I forgot to do map F. No, it's right. It maps a list of A to a list of B. And it receives a function. This function is what we call a callback, okay? It's a callback because it's going to be called back from map itself. So it maps A to B, and let's say I wanted to provide a function that does map to string, okay? And this would be a list, string of int, and list. And this function maps a list of int to a list of string. I can try calling it string list, saying 1, 2, 3, and it's gonna do exactly what you're thinking it's gonna do. But the interesting thing to think about it is how do we execute it? First, it's a recursive function. Second, it's like it's a higher order function, so it has a callback. Because it's a pure language, because this is a pure function, you may think about it as, okay, let's start here. So we can go here and we can say fun FL to this. My formatter is complaining about something. Oh, it should be 21 like this. No, oh my gosh, I hate this. Anyway, the important point here is when we do that, we can go on F, and then we can say, okay, F is going to be here. Okay, nothing changed here, same stuff here. Notice I removed the parameter and replace it by its argument. That's substituting it in place. But I can also do the same for the list. And here I can go list. And now I executed one step. What is going to happen? Now we are on the match. Now we are inside of the function itself. First, you can see that string of int map is still here, so we can keep going until map disappears. That's why it's recursive. As you can see, map appears inside of itself, but the method is the same. I can just keep going. So is it an empty list? No, it's not an empty list, which means this does not translate perfectly well. I will apologize, but it's because that's life. So we know that EL is going to be 1, that TL is going to be 2 and 3, and we start, and now we are here. String EL, it's going to be 1. TL is this. And then, as you can see, we can do the procedure again. We can keep substituting, but now we did one step of it. Now I know that the first answer is going to be the first element is going to be 1, but I'm going to keep going. I'm going to copy it again. Fun FL. And, oh right, I forgot, I deleted, it should be this. String of int, we can go again, remove all occurrences of F, and then do the parameter. Again, remove all occurrences of L, remove the parameter. Now we can see 2 and 3. It's time to reduce a match again. EL is going to be 2. TL is going to be the empty the list with 3. We remove the match, and we are here again. String of int of 2. It's going to be 2. TL, it's going to be 3. We did another step. I'm going to do it once more. Sorry, because I just want to finish it. but to say that on the last case there is nothing remaining, and that's why we call it the base case, which is when it stops. Again, F, L is gonna be here. Oh geez, simplifying code. Now we know tree. Just to be clear, a list is always like the element, which is this, followed by new, which is this. In OCaml we have this sugar, so those two are the same. Like you can see, as soon as I press Ctrl S, it formats. But yeah, that's the idea. So we know that EL is gonna be tree, and TL is gonna be the empty list. We are almost there. Now I can remove the match. String of int EL of 3, that's 3. TL is gonna be empty, so that's here. And the last step, we can go again. Fun. Doing this is not fun. Like you can do it on your head after a while, and that helps a lot. Like that truly helps, so you can understand the pattern. But yeah, here we can go. L is gonna be empty. Match of empty. And now here you can see that it's gonna be different. So this is this. We know that it's gonna enter on this branch. And that's it. So the answer of, I'm gonna do string list prime and string list, which is a map string to int, string of int. On 1, 2, and 3 is this. A good way to check if I'm right is to assert that they are equal. String list. And as you can see, it did not fail. I can also print it to show you all that they are the same. Here I can do string.concat, I think. String list, print in line, and string list prime. So you can see both of them are the same. This is how you can do for anything. In a strict language, you can always do this transformation. You just need to remember that when expanding it, you can never expand first here. You need to always go remove the parameter until there is no more parameter. That's like a total application. And as soon as there is no more parameter, then you start executing the body. If you do that by hand, you're going to be doing exactly what the interpreter or the compiler of the programming language is going to be doing. That's a simple thing. I think it's very, very important to understand it. Most people fail on this. It's also how you can think about let, for example. To finish it, I'm going to give an example of let. OCaml has a thing called shadowing. Essentially, shadowing means that you can do EL equals 1 and EL equals true. Those two are not, this is not mutation. This variable is not mutating to this. Okay? There is a very good way to show you, which is print and line. I'm gonna print EL. And here I'm gonna be doing callback here. Even if EL here is true, the answer is going to be 1. Why? Because first we execute the value of the let. So you can see that it printed 1. That's not mutation. If I was using mutation, OCaml has mutation, so you can do this. Now you can see that it's going to print 2. So those are two different variables. The good way to think about them is knowing that a let is just an expression that has a value and a body. So I'm actually going to be doing it here to make you guys' life easier. So this. First you can see that EL is not being used. I'm going to be printing EL1 and also EL2. As you can see, EL1, EL2, they have different values. But the good thing about it is, let's say you wanted to do it by hand, okay? So we know that EL is going to be 1. Sure. What do? We go on all the occurrences of EL. Again, that's if there is no mutation. If there is mutation, Ts breaks. And we replace EL by 1. But the thing is, TCL is different from this. So I have a table of names, and I do 1. So I know that CB is always going to print 1. And then I can go and I can say, okay, CB. I'm going to replace all the occurrences of CB. CB is this, this. Okay. Now we have EL2. EL2 is going to do the same thing. It's going to do this. And then we start here. And you may be like, oh, right. So here, it's an application, which means I can remove this and do this. Right. So I'm going to be executing this. And then this. So you can see that, sure, at the end there is a sequence of steps, but the original code, which was very different, still has the same property of you can just look in order, and by doing so it's gonna make sense, I guess. It's gonna work in your head. So here, yeah. You can see both cases execute the same. And of course there is a step where you cannot reduce. In theory you could reduce print, but there is this notion of a primitive. A primitive cannot be reduced. A primitive may be, it cannot be reduced through this process. So it may be an external function, for example. And yeah, there is nothing that you can do when you have an external function. But it's still good enough to arrive at the arguments and to understand the flow of execution of the language. This is not specifically to OCaml. That's going to be the same for JavaScript. That's going to be the same for C#, PHP, Ruby, any programming language. Not any programming language, most programming languages. Any strict language is going to have all the same behavior. You can keep going. There is a couple of differences when you have mutation. When you have mutation, you cannot remove the lets in the way that I showed you all, because that would change a couple of stuff. But if you don't have mutation, you can think about that, and you may be like, oh, but my language has mutation. Even if your language has mutation, most of your code is not going to be doing naive mutation. So you can just look on it and be like, okay, this can be simplified because this does not have mutation. And with mutation, you need to think about mutation in a slightly more general way and all, but yeah. That was it for today. I highly recommend looking at rewriting, looking at beta reduction for the lambda calculus, and also looking at Haskell, because Haskell does not behave like that. And by far, that's the hardest thing in Haskell. So if you can understand the difference between a normal strict language and Haskell, good job. But yeah, that was it. Thank you all for your time. Have a nice day. Bye-bye.